Here's a dimensional analysis question, which might be something that if you're a first-year engineering student doing something like fluid mechanics, this could be something that you might encounter in your assessment or in your exam even. So let's have a look at it, because I know typically dimensional analysis for students, when they see it for the first time, looks quite challenging, but at the end of the day, it's a sensible way of putting different variables together just to get a non-dimensional parameter in the end, which can be used to compare data from wind tunnel experiments as well as real life scenarios. So here's what we are dealing with. The question says that at low velocities, in other words, when we have laminar flow, the volume flow rate Q through a small bore tube is a function only of the tube radius, the fluid viscosity mu, and the pressure drop dp by dx. And then using the pi theorem, or the Buckingham pi theorem, find an appropriate dimensionless relationship for this. So the first thing I would suggest is write down all the variables. If you want, you can make a drawing, but it's not really necessary in this case. So you have your pipe, right? And then you have your, let's actually do it this way. And then we have a diameter, which is lowercase. Well, actually, the question doesn't tell us about the diameter, it tells us about the radius. So we have a radius r, we have a fluid viscosity mu, and then we have a certain pressure gradient dp by dx, and the volume flow rate is what goes in here like this. So let's write all the variables. We have q, we have r, we have mu, and we have dp by dx. In other words, we have four variables. And with those four variables, we're going to create our pi groups, okay? But before that, we're going to have to find what the units are. So for Q, we know that this is usually meters cubed per second, right? But I'm not going to use meters cubed per second. I'm going to say that, instead of meter, I'm going to use that as a length cubed, and instead of second, that's going to be time. So rather than using just SI units, I'm going to go even more general and say that, okay, that's a length cubed over time. Or I can just write this as L cubed t to the minus 1. Okay, then the other thing is that, what else do we have? We have radius. So we have the radius r, and radius is a length. So we just write that like this. This is length. And then we have fluid viscosity. Now, this is an interesting one. So fluid viscosity, typically, or dynamic viscosity more specifically, that's kilograms per meter second. So kilograms, that's mass over length times time. Note that this is not meters, right? That just says that we're looking at a unit of mass. And then finally we have dp by dx. So there's a pressure gradient. So the pressure gradient is pressure over meter. Okay, so let's actually see what the units are. So if you have pressure over meter, that is basically pascals over meter. Now pascals, that means Newton per meter squared over meter, which is the same as Newton per meter cubed. Okay, and Newton is kilogram meter per second squared over meter cubed. So that is kilogram meter squared second squared, or kilogram m to the minus 2 s to the minus 2. So that's it. And now the only thing I'll do is I'll just rewrite this in terms of, using the generic units of mass, length, and time. So that's going to be mass, then we're going to have length to the minus 2 and t to the minus 2, like this. And that's it. So we have four variables, and I don't think there's anything else in here. So we have the volumetric flow rate, we have the radius, mu, and pressure gradient. So then we count how many independent units we've got, and we have 3 units. And those units are m, mass, length, and time. So every single variable is expressed in terms of a combination of those three units, right? This is, for example, radius is just length to the power 1. Volumetric flow rate is length cubed times time to the minus 1, and so on. So, and actually let me write this as m L to the minus 1 t to the minus 1, just to be consistent. Okay, so that means if we have four variables and if we subtract the number of units, we're going to end up with the number 1. And this tells us how many pi groups we have. So we have one pi group, which I'm just going to call capital Pi. Not even pi 1 because there's only one of them. So we don't need to distinguish between multiple. So this pi group is going to have some repeating variables, okay, and one main variable. And the way I'll do this, although you can do this in multiple ways, obviously, is I'll treat those as my repeating variables, which means that my q is going to be to the power 1, and the other three variables are going to be to powers of a, b, and c. So we have radius to the power a, we have viscosity to the power b, and we have dp by dx to the power c. And this, of course, should have no units. Now, it doesn't really make sense to call those repeating variables because we only have one pi group, so we're not repeating the same structure somewhere else. But they work like repeating variables in the sense that we raise those to those dummy powers that we have to find out later. Okay, so let's do that. Now, Q has units of L cubed t to the minus 1, and then r the radius, that's just L to the a, and then viscosity is m L to the minus 1 t to the minus 1 to the power b, and then the pressure gradient is m L to the minus 2 t to the minus 2 to the power c. So this is going to be L to the 0, m to the 0, t to the 0. And as usual, we're going to separate the variables and find what a, b, and c actually are. So this is going to be L to the power of 3 plus A minus B, right? It's minus B and then minus 2C. So we have 3 plus A and then minus B minus 2C. There's going to be a bit of back and forth between the slides. And then we have M. So for M, we have B from here and then plus C from here. So we have just B plus C. And for time, we have T to the power of, so we have minus 1, minus B, and minus 2C. So minus 1, minus B, minus 2C, and that is equal to L to the 0, M to the 0, T to the 0. So all we do now is just compare each power. So the first equation will be 3 plus A minus B minus 2C equals 0. And then the next one is B plus C is equal to 0. And then minus 1 minus B minus 2C is equal to 0. So we have three equations and we have three unknowns. So from the second equation, we have C is equal to minus B, which we can sub in here. And this gives us minus 1 minus B and then plus 2b is equal to 0, so b is equal to 1 straight away, which means that c is equal to minus 1. And then we can use that to find what a is from the first equation. So that's 3 plus a minus b, which is minus 1, minus 2 times c, so minus 2 times minus 1. So 3 plus a minus 1 and then plus 2, that's equal to 0, which means a is equal to, we have minus 3 minus 2 plus 1, which is going to be equal to minus 4. So that's it. We have a is equal to minus 4. We have b equals 1 and c equals minus 1, which means the pi group is q. Now q has the power 1 as usual. And then our pi group is here. So we have r to the power a. So that's radius to the power minus 4. The next one is mu. So the dynamic viscosity to the power b, and then we have the pressure gradient dp by dx to the power c, like that. And that should be it. So the pi group is q multiplied by viscosity over r to the power 4 times dp by dx. So all this says is that this particular combination of parameters has no units. So another way of thinking about it is that because we used Q, our volumetric flow rate, as our main variable, in a way, this is sort of a non-dimensional form of that volumetric flow rate based on viscosity, radius of the pipe, and the pressure gradient. And that's it. That's the end of the question.